Okay, let's begin. And we're nearing the end of the wire here. It's, 3 more weeks, I guess. So we're going to spend this week on the next topic, which is a natural follow-up of what we have been doing in the previous chapter, which was the chapter on the second law. You remember one of the questions, one of the iClicker questions last week was which property is most commonly associated with the second law of thermodynamics, and the correct answer was entropy. But we haven't really learned anything in detail about entropy, so we're going to do that today. We're going to see how the second law lends itself directly to the definition of this property called entropy. So we're going to start first by looking at a few things, reviewing a few things. You may not know what a cyclic integral is, so I'm going to start by that. Have you seen that before? In math, maybe? So that's a cyclic integral. For us, so in thermodynamics, what this really means is that we're doing an integration pretty much like we do when we're calculating work or heat transfer. And we're doing that integration for the entire cycle. So we're going all around the path that the system describes as it goes through the different processes. So very simply, if you have a cycle, so here's a two-property diagram, any two properties, and then you have a system that goes through a series of processes. Maybe it starts here at 1, and it does different things, but eventually comes back, so that I can have many sub-processes making up my total cycle. And as you know, for example, if we break this down into sub-processes, say 1 to 2, and then 2 to 3, 3 to 4, 4 to 5, to 6, 7, and 8, and then from 8 back to 1. We have done things, for example, suppose that we want to find out what the work is for the process that takes us from state 2 to state 3. Then we could do, we could find that work. The work from 2 to 3 would be the integral from state 2 to state 3 of P dV, very simply. And we could also calculate, for example, if we're interested in the heat transfer, we could find, say, the heat transfer for process 5 to 6, so we would call it Q5-6. And we could also write it as an integral from 5 to 6. It's just that we don't have an expression to put in here other than to integrate the actual differential Q as I go from 5 to 6. So those are two examples of two integrals, one to calculate the work, another one to calculate the heat transfer for a portion of the cycle. But suppose that I am interested in calculating the integral for the entire cycle. So suppose that I am interested in finding, I will call it Q cycle, and I'll make it the integral for the cycle of delta Q. Suppose that I want to calculate that. That means I really want to find all of the heat transfer amounts for all of the individual sub-processes until I complete the cycle. So if I wanted to do this for this cycle, then I would have to do all the individual integrals. So I would have to do, this would be equal the integral from 1 to 2 of delta Q plus the integral from 2 to 3 of delta Q, and so on. Do all of them until I do the last one, which would be the integral from 8 back to 1 of delta Q. And that would be my Q cycle. Yes, sir?
Does this imply that cyclic integrals apply to reversible processes?
No, I haven't made any distinction. This is any process, right? Any process. We haven't really said whether this process or this cycle as a whole is reversible or not. I'm just doing a calculation of the heat transfer. For example, if I do this, I'm adding up all of the heat transfer contributions for each of the sub-processes, so I get the total, the net heat transfer for the cycle, and I could do the same thing for the work. So let's say that we're going to do this calculation, but we're going to do it for a Carnot cycle. So we're going to do exactly this, but for a Carnot cycle. Let me put all this stuff here somewhere. So let's say that I do a Carnot cycle. So I'm going to sketch a Carnot cycle. Right. And because it's a lot easier to put a Carnot cycle, we have seen a Carnot cycle, for example, on a PV diagram, but let's do a Carnot cycle and let's put it on a TV diagram. Remember, the Carnot cycle is made up of 4 processes. 2 of them are adiabatic, and the other 2? Isothermal. Right? So 2 adiabatic and 2 isothermal. So because it has 2 isothermal processes, then it's convenient to put it on a TV diagram because we know 2 of the processes are going to be horizontal lines. So if I put it here, my Carnot cycle would look something like this. Here's one of the isothermal processes. And then here is one of the adiabatic processes. And then back to isothermal, and then back to adiabatic. So let's say that I start here. 1, 2, 3, 4, and I'm going clockwise. So that's a Carnot cycle, for example, representing a heat engine. If I run it backwards, then it would be a refrigeration cycle. But in either way, it's a Carnot cycle. But here I have it forward, so I have it as a heat engine. And suppose I want to do what I just told you. Let's say that we want to calculate the Q for the cycle. So I want to find the Q for the cycle, which is going to be the integral for the whole cycle of delta Q, which is going to be, if I break it down, let's just do it on the next line here, is going to be the integral from 1 to 2 of delta Q plus the integral from 2 to 3 of delta Q plus the integral from 3 to 4 of delta Q plus the last one, integral from 4 to 1 of delta Q. And that would be my cyclic heat transfer for the entire cycle. So now let's look at some of these integrals and see if we can simplify this a little bit. Can we simplify something here? Let me try him right there. Those 4 integrals, can you simplify any of them? Okay. Somebody wants to try? Yeah?
Can you simplify 2 of them?
For example, tell me what you want to do.
Combine the adiabatic cycles and isothermal.
Combine them? But I don't want to combine them. I want to leave them separate like they are right now.
Isn't delta Q0 for 3 to 4 and 1 to 2?
Let's see. 1 to 2 is adiabatic, right? 1 to 2 is adiabatic. So we know there is no heat transfer there. So the simplification that I had in mind was, like he said, this one is 0. Right? And the other one that he's saying is 0 is 3 to 4 because that's also adiabatic. So my 4 integrals boil down to just 2 integrals. Right? 2 of them are 0 because of the process being, this being adiabatic here and this being adiabatic there. All right, how about the other 2? Let's look at the first one. The integral from 2 to 3 of delta Q. Does anybody know what that might be? Nope. Anybody raise a hand?
Just delta W?
if you're saying that that's delta W, you would be saying the following. You would be saying that as I go from 2 to 3, there is going to be a certain heat transfer. And you're saying that that's equal to the work in that process. You're saying that the heat transfer from 2 to 3 is equal to the work from 2 to 3. That would imply that the internal energy between 2 and 3 did not change, the delta. Because if you look at the first law, right, you're saying the following. Let's write the first law down here. Delta U equals Q minus W. And we can apply it between any two states here. So if you're telling me that this integral of delta Q from 2 to 3, which is the total heat transfer between 2 and 3, is equal to the work between 2 and 3, you're telling me that this is 0. But I can clearly see that these are two different states. Right? So in general, that might not be 0. Back there? Well, if you bring in R in, you're thinking that this is an ideal gas. Right? And I'm not saying that this is an ideal gas at this point. Anybody else? Okay, yes.
Would it be the difference of the specific volumes times the high and low temperatures?
No. No. Let me help you a little bit more. Let's draw let's look at the, if I can find it quickly, what this Carnot cycle might look like. Let's see, second law. Here it is. All right. So here are the processes. One, in fact, they hopefully match. They do. The numbers match. So here is 1 to 2, this compression, which you already knew it was adiabatic. We labeled it such. And then 3 to 4 is this expansion here. It's also adiabatic. So the ones that we're left with are this one, this isothermal expansion from 2 to 3, and then this isothermal compression from 4 to 1. Now this new diagram that I put here gives you the answer to my question. What's the integral from 2 to 3 of delta Q?
The heat going in.
Which is Q sub H, right? So because we should have known that the heat added during process 2-3, which is the isothermal expansion, happens to be Q sub H. That's the heat that was added to the system. So what this is saying, let's just put this in a box here, leave it aside. This is just the first law. That this integral right here is Q sub H. So if I keep working my expression down here, 0, then Q sub H, and then the last one is Q sub L, right? But we know that's coming out of the system, so we know it's negative. That integral will come out negative. The integral from 4 to 1 of delta Q will come out negative, and it will be Q sub L. So what we just found out is that if I'm interested in computing this integral, so let's put what we started with. This is the integral, the cyclic integral of delta Q for this heat engine, which is this Carnot cycle. So we get this result. Well, I say, well, that's interesting, or maybe yes or maybe not. In fact, one thing is very interesting, because what is QH minus QL for the cycle? This is the net. We were calling this is Q cycle. Is the net heat transfer for the cycle, and what's that equal to? This is equal to the work, because now, as opposed to my previous question, it was just for a process. For the entire cycle, indeed, delta U is 0. If I go all the way back to the initial point. So in that case, of course, this is also happens to be the network. Okay. Any questions about this? This was just warm up. What we really want to do is something else, another cyclic integral. So the one that I really want to do is the following. I'm going to do another cyclic integral. But this time I want you, for the same cycle, for the same Carnot cycle, I want you to find, I'm going to make one change here. I'm going to introduce the temperature there in the denominator. So rather than finding the cyclic integral of the delta Q, I want to find the cyclic integral of delta Q over T. And we're going to proceed exactly the same way. So we're going to say integral from 1 to 2 delta Q over T plus integral from 2 to 3 delta Q over T plus integral 3 to 4 delta Q over T plus integral 4 to 1 delta Q over T. All right? Okay, so this is different from the previous one, but there is some similarities, right? Because if I look at the integral from 1 to 2 of delta Q over T, what is that equal to? Huh? Here's the cycle again in the TV diagram. What about the integral from 1 to 2 of delta Q over T? That's still a big zero because there is no heat transfer. So there is no heat transfer. That is going to be 0. So I can still, like before, I can cross this one out, is adiabatic, and also cross this one out because it's adiabatic. So I'm like before, I'm left with 2. The integral from 2 to 3 delta Q over T and integral from 4 to 1 delta Q over T. So let's look at the first one of those two. The integral from 2 to 3 of delta Q over T. The nice thing is that T that appears in that integral is constant, right? That T is constant, so I can take it out. So if I take it out, and of course it's this one here. Let's label this here, T sub H, T sub L, right? So what is that first integral then? QH over TH, very good. And the other one that survived, the integral of delta Q over T from 4 to 1 is equal to what?
Negative QL over TL.
QL over TL, but negative, right? Because that's going to be heat coming out. So it'll be minus, QL over TL. All right? So that's what I get. So let's use the minus sign to get rid of it. So QH, TH minus QL, TL. The next part requires for you to really be on top of things to fill in the right-hand side of that equal sign. Who is on top of things? Anybody? Nobody. What do you think it is?
Delta S.
No.
We use the ratio
Don't ask me a question. I want an answer.
TL over TH equals Q over QH.
Well, tell me what you want to say then. I just want to know if you know it. Then I'll explain it. No. Anybody else? That side, back there? Last person? No? You have to know.
I remember we talked about last week. Does that have to do with efficiency?
Nah.
No?
No. He was the closest. What were you saying?
Use the ratio T.
What do we know about a Carnot cycle that is ideal, right? It's an ideal cycle. Because it is an ideal cycle, what is QL over QH for a Carnot cycle? TL over TH. We know this. This is, in fact, what defines the absolute temperature scale. We know that. So what's the answer? 0. All right? So the answer was 0. Right? Because of that is written there. So this integral happens to be 0. All right? Okay. So let's put that here somewhere in summary. The integral of delta Q over T is equal to 0 for Carnot, because we're doing this for a Carnot heat engine. Heat engine. All right? Okay, now I'm going to switch my engine, and now it's going to be a real heat engine. Okay, so I'm going to redo this calculation now. Now it is a real heat engine. Okay? It's a real heat engine. But it's going to be operating the same way. Well, I shouldn't say I'm sorry. It's going to be operating exactly the same way. So it's going to be still 2 adiabatic and 2 isothermal. But it's a real heat engine. So, but it's still 2 adiabatic and 2 isothermal. So what happens when I do my integral for the whole cycle? Right? Let's see what changes. If we go back here to reuse these results, right? Since I still have the 2 adiabatic processes, this is still true. So this doesn't change. Right? And what about this? 2 to 3 and 4 to 1. That doesn't change either. Those are still isothermal. So it's still the same cycle. It's still this. It's just that in the first case, I said this is going to be ideal. Going to be all reversible processes. But now I'm saying, well, now this is the real system. But I still want to make it adiabatic from 1 to 2 and 3 to 4. And I'm still going to make it isothermal from 2 to 3 and from 4 to 1. So what I'm saying is that this part doesn't change. All these results that we got to this line are the same. QH, TH minus QL, TL. So really the only thing that is changing is that now this is not true, right? So in fact, you may want to say here, when I said because this, for an ideal cycle. That result that the ratio of the Q's is the ratio of the T's is only valid if it's an ideal cycle. But now it's real, so that's not true anymore. So what is this going to be? Let me make your life a little easier. Let me draw a comparison of these two cycles in a cartoon. I'll come back to that. So here is the Carnot. All right? And here is the real. Okay? But they are both going to be, to make our life easier in understanding what's going on, they're going to be receiving the energy, the heat from the same reservoir. Okay? So I'm going to have that and that. And in fact, I'm going to make it the same. So this is QH, QH. I'm going to make those the same. So I'm going to feed my real engine the same amount of heat transfer as I fed my Carnot engine. And I'm also going to make them reject heat to the same low temperature reservoir. Right? So anything that is labeled there is the same. The TH is the same for both. The TL is the same for both. And the QH is the same for both. And so here is the real work. And here is the Carnot work. Right? What can you tell me about those two?
One's 0, one's not 0.
Which one is 0?
The Carnot.
What is 0?
The work.
The Carnot out of the work cycle of the. Then we should trash that Carnot cycle because it's not giving us any work, right?
Is the QL 0?
No, the QL is not 0. I haven't written any QLs yet because I'm going to go step by step. Whoops. So I just want you to compare the work. The Carnot work is greater, right? Because the Carnot heat engine is the most efficient of the two. For the same heat input, the Carnot will deliver more. So I know this. Right? I know that much. Now you can tell me about the QL. QL Carnot, QL real. Which one is bigger? QL real, by simple energy balance, right? So QL real is greater than QL Carnot. All right? This result is from the first law. And of course, this one is the second law. Right? All right, so now let's answer this question. QH over TH minus QL over TL. What is that? Put together this. Let me move this up a little bit. We don't need that much up there. But we want to see this whole thing. What's the answer to?
Would it be less than 0?
Less than 0 is the correct answer. Yeah? So the correct answer is that this is less than 0. All right? Everybody sees why? Is there anybody who doesn't see why? Okay, let's tell them why. You agree that for the Carnot this was 0. You saw that, right? For the Carnot heat engine this was 0. And in this case I said everything is the same Q sub H, the same T sub H, the same T sub L. The thing that is different is the Q sub L, which for the real cycle is larger. This number is bigger. So if it was 0 for the Carnot cycle, it has to be negative for this one, because you're subtracting a larger number, right? So what we find then is that if we summarize again what we just did, that the cyclic integral of dq over t is less than 0 for a real heat engine. And we want to contrast that, in fact I'll put it here, with the previous result that the integral of dq over t was equal to 0 for a Carnot heat engine. All right? That result is very important. And in fact, we haven't seen really any equations yet for the second law of thermodynamics. But if you were to write an equation for the second law of thermodynamics at this stage of the game, that would be it. Right? So what we do is we write it like this. We summarize these two into one result. We say the integral of, let me move this away. The integral of delta Q over T is less than or equal to 0. Okay. And we call this the Clausius inequality. Clausius inequality. And you have to know, of course, when it's less than and when it's equal. But you know that it's in the lines above, right? So the integral of delta Q over T is less than or equal to 0 is a way to write the second law of thermodynamics, because the result came from applying the second law. If you go back, to find that it was equal, we applied this, which is it comes from the second law of thermodynamics, the definition of absolute temperature for an ideal cycle. And the less than comes from the second law of thermodynamics because it came from this comparison, which is using the second law of thermodynamics. So this is the Clausius inequality. Less than 0 for any real cycle, equal to 0 for an ideal cycle. However, keep this in mind, ideal cycles don't really exist. Carnot cycles are just an imaginary cycle. So that means that for any real cycle, the integral of delta Q over T is less than 0, always. So this is the second law of thermodynamics, one way to write it as an equation. All right, any questions? So now, let's see how this leads to the property called entropy. It has to do with that integral. Some of you, I guess, because you had, when I first asked, a couple of you brought up entropy. You know, when I said, what is the integral delta Q over T for the cycle? So as you have seen, it had nothing to do with entropy, but there's something about it that has to do with entropy, so let's do that next. So let's do something similar to what we did a while back. I'm going to do a cycle. I'm going to look at a cycle on a property diagram. I'm going to make it arbitrary like I did a while ago. So this is any two properties of your choice. And I'm going to do a cycle that has two sub-processes. So here's one. I'm going to go there. And my states will be 1 and 2, and then, of course, back to 1. So I will come back to 1. That's a cycle. It's not a Carnot cycle. It's a cycle. Any cycle. It has two sub-processes. And but I'm going to do the following to begin with. Let me label this path. So I'm going to say this is path A, and I'm going to label this path B. All right? And I'm going to say first that this is a reversible cycle. So pretend that this is a reversible cycle. So that means it's ideal. And let's do the following. Let's do the integral that we just computed. So let's do the cyclic integral. That means I'm going to go from 1 to 2 and from 2 back to 1 of delta Q over T. And just like I did for the previous example, we were looking at a Carnot engine. I'm going to break it down into the two parts. So it's going to be the integral from 1 to 2 of delta Q over T plus the integral from 2 to 1 of delta Q over T. But I'm going to have to be a little bit more careful here because I want to specify the path. Because obviously I can go from 1 to 2 on any path. And I pick this A path and I'm returning on path B. So to make that distinction, I'm going to put it here with a comma. I'm going to say I'm going on from 1 to 2 on path A and I am returning on path B. All right? And now I'm going to do the following. I'm going to go there on a different path. So I'm going to write another path. Actually, let me do it the same color. I'm going to have another path here that goes from 1 to 2 that I'm going to call C, path C. Also reversible. So everything is reversible. Any path that I take for this process is reversible. So I now have another situation where I'm going to do a cycle, but this time I'm going to go on C and come back on B. All right? So what happens there? I'm going to do the integral for the cycle, dq over t. Now I'm going to get integral from 1 to 2, delta q over t. But now I'm going on path C. And then I am going to return from 2 to 1 on the same path B, delta q over t. So I have written that Clausius expression for the cycle, the cyclic integral, for the two cycles. One goes on A, the other one goes on C. Now, what do we know this is equal to, the first one? What is the first one equal to? 0. Because I should tell you that even though I did it for a reversible a Carnot cycle, the result that I got is the same for any ideal cycle. So this is 0. We just proved it for the Carnot heat engine. And this, of course, is 0 too, because I'm going also on a reversible cycle. So now let's take these two expressions, these two equations, and subtract them. Right? So I'm going to take, for example, the second one and subtract it from the first one. What happens? So this right here, subtract. Then I have to write these out because these are different integrals. 1 to 2 on path A, delta Q over T, minus 1 to 2 on path C, delta Q over T. Right? But these ones, when I subtract, they cancel out because these are actually exactly the same. The integral from 2 to 1 on path B, integral from 2 to 1 on path B. So these are 0. This minus that is 0. And of course, on the right-hand side, I still have 0. So I have that, which if I now flip the second term to the right-hand side, I get the integral from 1 to 2 on path A is equal to the integral from 1 to 2 on path B of dq over t. That's what I get with this little exercise. Sorry, thank you. C. All right? Good, I think you're following then. So I find this by doing this little exercise, that the integral from 1 to 2 of dq over t is, on path A, is equal to the integral from 1 to 2 of delta q over t. And in fact, on D, F, H, any path, as long as the only condition that I imposed on any of these paths is that they are reversible. That's the only condition that I imposed. But it doesn't matter how I get there. So what this is telling me is that this is independent of the path. So this integral from 1 to 2, I can write as a conclusion that the integral from 1 to 2 of delta q over t is independent on the path. Right? So I have an integral of something between 1 and 2 is completely independent on the path. Right? Independent of the path. Doesn't matter how I get there, I'm always going to get the same result. So what that means, of course, is that this quantity that I could call it, this is some differential. I could call this the differential of something. That something has to be what type of a quantity? Not the name of it, which you might already start guessing what it is, but what type of a quantity in thermal? No. The delta, that something between 2 points 1 and 2 is completely independent of how you get there. The delta of that quantity only depends on the states, on the two states. That means that that something is what? A property. A property. So whatever it is that this is representing, right, on this reversible path, that's the only condition, is a property. And that property is what we call entropy. So putting it all in one line, and of course the integral from 1 to 2 of ds is delta S, or S2 minus S1. So we can write S2 minus S1, the difference in the property of entropy between those two states 1 and 2 is the integral from 1 to 2 of delta Q over T. The only condition is that it had to be, we did it on a reversible path. So long as we do it on a reversible path, that quantity that we compute represents a property. So we just come up with this new property that we call, of course, entropy. In this case, of course, is an entropy change, okay? Because it's a delta S. What are the units of this property? What are the units of this property? By matching sides, it has to be the same units as heat transfer divided by temperature, right? So heat transfer would be, if it's SI, you could do joules or kilojoules, and temperature absolute Kelvin. So those are units of entropy. Kilojoules or joules per kilogram per Kelvin. So keep in mind, it's just units of energy divided by units of temperature. If you want to write it in another system, that has to be the units. So now we have a new property to deal with. And fortunately, the last one that we need to worry about, but we can add it to our bag of properties. And what that means is that when we do property diagrams, right, then we can include entropy as a property. So the ones that we started working with at the very beginning of the course, PV, TV, those are the ones that we have used the most so far. Now we have two new properties. One came out earlier, which was enthalpy. And of course, now we have entropy. So you shouldn't be surprised that you're going to start seeing diagrams using these other properties. Let me show you what they look like, just so you have an idea of some of the most common ones that you're going to see from this point on. An interesting one is precisely a plot of, well, let me show you this one first. You could do a TS diagram. That actually happens to be, as you will see in a moment, quite convenient. But let me show you what it looks like. Don't panic about the how busy this one is, because it's just so many lines. But I'm not wanting you to read all of these lines by any means. But just to show you what a typical TS diagram looks like, this is a TS diagram for water. So you see some of the features that you have seen before in other diagrams. So you see the dome there. This orange region is the dome with the critical point at the top, and the saturated vapor line right here, and the saturated liquid line right there, a little shorter. So that's temperature versus, this is lowercase s. So just like you have extensive and intensive properties, entropy, you can also have extensive and intensive. If you do it per unit mass, is intensive. And so here, what I did is this red line is to show you what an isobar looks like on a TS diagram. It's not very different from the isobar on the TV diagram. Right? If you remember the TV diagram, the isobar, of course, was horizontal inside the dome and then went up. Same thing. These diagrams are useful when you're dealing with mixtures that have liquid and vapor and have high quality, in fact. You cannot see it yourself, but there is a quality line here that I am trying to find. I cannot read it myself. But usually these are really high quality values. Or superheated vapor. Of course, you have a lot of space here for the superheated vapor. Where you don't really have a lot of space to see anything is in the compressed liquid region. So this type of diagram is really useful for us when we're dealing with a high quality mixture or with a superheated vapor. So that's one, a TS. I'll come back to this one in a second because this one is useful for something that we have seen. But I'll show you another one. So that's the TS. And the other one is the HS. And this one is a little easier to see. That's an HS diagram also for water. So now it's enthalpy versus entropy. The dome is still there. The same features as before. So the compressed liquid region is actually very small and very hard to see. You use these diagrams, again, when you're dealing with superheated vapors or with high quality mixtures. This one does have the quality easy to see. These lines, let me zoom in here in the dome. You can see quality lines here. So for example, this one is 98%, 96%. The last one that is shown here is 80%. So that's 80% quality. So if you have something like 30% quality, this wouldn't be useful. Or if you have compressed liquid. But anything of higher quality or superheated is very nice to see here. This would be very useful also, the HS, when we go into the next chapter, the last chapter, which we're going to see later. So for now, just know that these charts exist, combining these properties in particular, bringing in the entropy into the equations. If you have a mixture, it's just the same as we have seen before. So if you have a mixture and you look, for example, into the water table, you will see that also the values are given for the for a mixture of liquid and vapor, a saturated mixture. The entropy calculated using the quality, the same way we did it earlier for the specific volume or for the internal energy or for the enthalpy. You can use it, you can calculate it for a mixture using the quality, just like before. Does anybody have a question? No hands? Okay, let's see. Let's do something interesting here. All right, so let me write again. Running out of paper here. Let me write again this result. Right? So we just found that delta S is equal, whoops, all you see is a big hand there. Delta S is equal to the integral from 1 to 2 right, of delta Q over T for a reversible process. So that we still have that warning label here. All right, for a reversible process. So now let's go back and think of the Carnot cycle one more time. All right? Remember, the Carnot cycle is 2 isothermals and 2 adiabatic. Right? And we have seen it, that it looks like where is let's see, right there. When we plotted, for example, on a TV diagram, it was convenient because the 2 isothermal processes on the TV diagram will be horizontal lines. But suppose I now ask you, let's plot the Carnot cycle on a TS. You guessed correctly. On the TS diagram. So here's T, here's S. What does it look like? Huh? A box. It looks like a box. Right? It looks like a rectangle. Why is that? So if I put it here, here's an isothermal. In fact, 1, 2, 3, using the same notation as before. 1, 2, 3, 4. That's what that cycle looks like. This is what it looked like on the TV diagram. This is what it looks like on a TS diagram. Does everybody see why? Is anybody who doesn't see why this became a rectangle? Why is it that the two adiabatic processes became straight vertical lines? Is written right here, right? So here is adiabatic, adiabatic, isothermal, isothermal. All right? The two adiabatic processes become delta Q is 0, delta S is 0. Right? Become constant entropy processes, or what should we call that? An isentropic process. If the entropy doesn't change, that's an isentropic process. So there you have another iso something. You will see isothermal, isobaric, isochoric, isenthalpic if the enthalpy doesn't change. So isentropic, entropy doesn't change. So let me ask you a question now. Does that mean that the process was adiabatic? Those two processes were adiabatic, and they're isentropic. Does that mean that every adiabatic process is isentropic? Is every adiabatic process isentropic? Only if it is reversible. Right? Only if it is reversible. Because that's a condition that we imposed on this equation. That delta S is the integral from 1 to 2 of delta Q over T if it is reversible. But that, now we can say that for sure. If a process is both adiabatic and reversible, then it is isentropic. So it has to be both at this point. It has to be both adiabatic and reversible, and then it'll be isentropic. Okay. What about let me do a couple of things. Well, let me first ask you a question. What do you think this area represents inside this box, inside this rectangle? What is the area in the box? Delta Q?
Yeah.
A delta with a little delta or a big delta? Be careful, you're going to slip. Huh? It's not a delta, first of all. Not the little or the big. Huh? I don't like change, though. The word change. But you got the point. This box is what I called earlier today Q cycle. It's not a delta Q. Remember, delta Q is not a good word with the capital delta. So this box is Q cycle. Or you can also refer to it as Q net. Right? is the Q net, which of course is what? What is Q cycle or Q net? Not yet. That's true, but in terms of the high temperature Q and the low temperature Q. Not yet. That's true, but what I want to say is this. Right? That box, that area in the box represents the cycle work, which is QH minus QL. True. It's a cycle. So if we look back at the first law, delta U is 0. So indeed, this is W cycle. Right? Because it's a cycle, there is no delta U. There is no change in energy. So that box represents the net heat transfer or the net cycle, but it also represents, by virtue of the first law of thermodynamics, it also represents the net work out of the system. Where does that come from? It all comes from here. Because if you write this equation for a differential, you can write this same thing as ds. ds is delta Q over T. Because if I go ahead and integrate this, the integral of ds from 1 to 2 is delta S, and then here I have the integral from 1 to 2 of dq over T. So this is obvious, that I can write it either as an integral or I can write it like this. But if I write it like this, I can of course say that dq is T ds. Right? And if I now integrate this, instead of the previous version of it, if I integrate this, then this is Q12. And it's the integral from 1 to 2 of T ds. And that's why, of course, then Q12 becomes the area under the curve. So if this was the process from 1 to 2, and this is T and this is S, then indeed this area under the curve, right, is indeed Q12. Right? So that's where that comes from. So when you go back to this, let me move this to the bottom here so you still have it there. But that's why this integral, that's why this box is the net heat transfer. Because the integral from 2 to 3 would be the area under that curve all the way to the bottom, but then you're going to be subtracting the area between 4 and 1, so the area under the second line at the bottom, and then you're left with only the area in the box. Yeah. Okay, let's do a quick example using some numbers and these concepts. Any questions about any of these concepts from today? Okay, let's do one example that I have here. So, and this is very similar to a problem in your homework. I think some of the numbers are different, but this example is similar to problem 636. I think the difference is that some of the numbers have changed. So what this problem has, or what it says, is that we have a Carnot refrigeration cycle. So Carnot refrigeration cycle involving refrigerant 410A. All right? That's my substance. Okay, and what the statement says is that the refrigerant the cycle operates between a TH of 40 Celsius and a TL of minus 5 Celsius. So just a little below freezing for water and higher than typical room, a very hot summer day. So that's the TH and the TL. And the problem also says that during the heat rejection cycle, cycle process, so during heat rejection process, the refrigerant goes from saturated vapor to saturated liquid. Okay. During the heat rejection process, the R4110A goes, let's just simplify by saying, goes from saturated vapor, so G, to saturated liquid, F. Right? And then it asks us to find a few things. It says find the qualities, right? The qualities at the beginning and end of the heat addition process. All right? So, 410A between 40 Celsius and minus 5 Celsius. We know that when it rejects heat, so when the refrigerant, when you remove the heat from the refrigerant, it goes from saturated vapor to saturated liquid. And you want to find the quality at the beginning and the end of the heat addition process. And I think it also wants you to find the coefficient of performance. Right? So you have to find those things. Okay, so it's a Carnot refrigeration cycle to begin with. So remember, a Carnot cycle running forward is a heat engine, running backward is a refrigeration cycle. So that means that it looks exactly like the one we just drew. We don't have to go very far. It has to look like that. For example, if I put it on a TS diagram, it's just that it's going to be running the other way. So if I sketch it on a TS diagram, and let me make it lowercase, because I'm going to have to look up properties, then it has to look just like that. But it's running the other way, so. And here's the TH that was given, and here's the TL that was given. All right. My first question to you would be, where is the dome? If I want to add the dome to this TS diagram, where do I put the dome? The key to the answer, of course, is in the sentence that says, during the heat rejection process, the refrigerant goes from saturated vapor to saturated liquid. Which of those four processes, let's label them with numbers. 1, 2, 3, 4. Which one of those four is the heat rejection process? Which one? 1, 2, 4. It's backwards from a heat engine, right? If it was a heat engine, it would be running clockwise. You would be adding heat at the high temperature. But it's a refrigeration cycle. It's running backwards. So the heat rejection is where? Which one? 3 to 2. Oh, except I messed up by putting those numbers like that, but we'll just have to live with that. That the numbers kind of don't go in order. Because if it was a heat engine, it would be 1, 2, 3, 4, but we're running it backwards, so it goes 1, 4, 3, 2, 1. So that's okay if we can live with going backwards. In fact, it might be useful because it sort of reminds you that it's running backwards. So that means that when you go from 3 to 2, that's where you actually have the heat rejection, right? So you can write here Q sub H, right, is Q3, 2, right? That's when you take the heat away. And down here, of course, is where you add the heat, Q sub L. So Q sub L is Q 1, 4. All right? So we have to establish that fact. And now we can put the dome. Where does the dome go? It intersects the box where? 2 and 3, correct. So if I want to put a dome here, I know it has to intersect here and here. So I'll do something like that. All right? Okay? That's my dome. All right. So, of course, what they're asking me are the qualities during, at the beginning, at the end of the heat addition process. The heat addition process is the QL. So what they're asking me to find is quality at 1 and quality at 4. Right? Now I have established that I need to find those qualities. All right? Okay, so, of course, I know the following. I know that the entropy at 1 is the same as the entropy at 2. Right? And I also know that the entropy at 4 is the same as the entropy at 3. Right? I know that. And what's the entropy at 2? That's going to be SF, right, at 40, right, Celsius. And what's going to be S3 is going to be SG at also 40 Celsius. So I can get those from the table. Go to the table, get these numbers, right? SF and SG here, there. And then, of course, I know those are actually the entropies at 1, at 4, respectively. Right? And so once I know the entropy at 1, and I know the entropy at 4, I can go back to the table to read SF and SFG, but now add -5, right, to get my quality at 1, at 3. So I'll let you finish that. What about the coefficient of performance? How can I get the COP? The key is that it is a Carnot cycle. Right? Because it is a Carnot cycle, we have that if we have all the temperatures, we have what we need, because right? we know the ratios. So because it is Carnot, I know that COP, which is always for a refrigeration cycle, Q sub L over W. But of course, W is Q sub H minus Q sub L, right? And I can, because of the temperature ratio being equal, I can immediately replace this expression with this expression. Just because the ratios are the same, right? So since TL over TH is QL over QH, that's true. And since I have all the temperatures, I can find the COP. I just have to remember that I have to put it in Kelvin when I plug the T sub L. Well, here it doesn't matter because you're subtracting, but here you have to put it in Kelvin at the top. But those are all given, so that's easy. Okay, how are we doing on time? Maybe I just ask you a couple of questions. So let me see if anybody has a question first about this problem. Okay, let me ask you, I brought a couple here. Okay, so while we get ready, this should bring up that. That's the last question from last time. So are you ready? Okay, I'll bring the first one. So we saw this today. For the same TH, TL, and QH, the QL of a real heat engine is greater than, equal to, or less than the QL of an ideal engine. So 5, 4, 3, 2, 1, 0. The QL of a real heat engine is indeed larger. Right? It rejects more heat. We saw that at the beginning of the lecture today. It rejects more heat than the ideal one because the ideal one delivers more work. So there is more heat to reject in the real heat engine. All right, let's do another one. Okay, this diagram represents an ideal gas cycle. So this is for an ideal gas. Which cycle is this? Carnot, Rankine, Brayton, refrigeration cycle, or none of the above? So you may have to go back and look in your notes unless you remember. Okay, 5, 4, 3, 2, 1, 0. Which one is it? Yeah, it is a Brayton cycle. Couldn't be a Carnot cycle because if you look back, so for those who answer Carnot, let me move this out of the way here. You can see that this is a PV diagram. So from 2 to 3 is isobaric, and from 4 to 1 is isobaric. So it couldn't be isothermal at the same time if it's an ideal gas. So, so that rules out Carnot. Now, the Rankine cycle and the Brayton cycle are the same in the sense that there is 2 isobaric and 2 adiabatic. What rules out the Rankine cycle here is that they're telling us that this is a gas. And a Rankine cycle is for a mixture of liquid and vapor. So that leaves the Brayton cycle as the answer. It's running forward, so that rules out a refrigeration cycle because it's running in the direction where it delivers work. Okay, and the last one, I think, is an easy one. What are the units of specific entropy in SI? Kilojoules per Kelvin, kilojoules, kilojoules per kilogram Kelvin, kilojoules per kilogram, or none of the above? All right, 5, 4, 3, 2, 1. Some people left. There. Yeah, so specific, so it's per unit mass. Units of entropy are kilojoules per Kelvin, but per unit mass, you need the kilogram. All right.